Nature doesn't do perfect angles, but the Hubble Space Telescope just found them anyway. I'll be honest, what I'm about to show you shouldn't exist deep inside the hazy glow of the interstellar visitor 3I Atlas. Hubble has revealed three distinct jets of material erupting in a perfect equilateral triangle. They are spaced at exactly 120 degrees, a mathematical symmetry so precise that the statistical probability of it being a natural fluke is just 0.2%. That's a 1 in 500 chance. We went looking for a comet, but the geometry we found looks like architecture. It's the kind of discovery that changes everything we thought we knew about the rocks drifting through the void. But here's the part that really messes with my head. If this isn't a miracle of physics, then we're looking at a deliberate signature. Welcome back to the darkness. This is the mystery of 3I Atlas. For months, we've watched this object drift through our system, assuming it was just another silent traveler from the stars. But as it gets closer to us, the Larsen-Sekanina filters have peeled back the layers of dust to reveal a core that defies conventional science. We are no longer just talking about ice and gas. We're talking about a structure that seems to be stabilizing itself with surgical precision. Is it a strange new class of comet? Or is the 0.2% probability telling us that we aren't alone in this silence? Today, we investigate the impossible geometry of 3I Atlas, the data that has astronomers divided, and what might happen when this visitor finally reaches the king of planets. When we look at the stars, we often forget that we are looking through a veil. Space is vast, but it's also crowded with dust, light pollution, and the limitations of our own technology. To see 3I Atlas clearly, we needed something beyond the ordinary. Between November and December of last year, the Hubble Space Telescope was pointed toward a tiny point of light moving against the backdrop of the deep void. It captured 17 images. At first, the raw data was underwhelming. If you saw the original files, you'd probably just see a blurry white smudge, the kind of thing you'd ignore if you weren't looking for it. That smudge is the coma, a massive cloud of gas and dust that surrounds the heart of 3I Atlas as the sun begins to cook its frozen surface. But astronomers aren't satisfied with blurs. Truth is hidden underneath. To find it, they used a specialized tool called the Larsen-Sekanina rotation gradient filter. Think of it like a digital sieve. It filters out the chaotic noise of the dust and highlights the structures that are actually moving or rotating with the object. When they applied this to the Hubble data, the smudge vanished, and what emerged was a pattern that sent shockwaves through the scientific community. Instead of a messy explosion of gas, they saw three distinct needle-thin jets. And these jets weren't just random leaks. They were positioned with the kind of balance you'd expect from a manufactured drone or a deep space probe. I can't shake the feeling that we are looking at something that was built to stay stable even in the middle of a chaotic drift through a foreign solar system. Let's talk about that 0.2%. In the world of science, we usually look for a sigma value, a level of certainty that tells us we found something real. But what happens when the math tells us that what we're seeing is almost impossible by accident? In nature, symmetry is a rare guest, usually reserved for the microscopic world or the biological one. You see it in the sixfold beauty of a snowflake or the radial petals of a flower. But on the scale of a mountain-sized rock hurtling through the vacuum of the void, it's almost unheard of. The three jets detected on 3I Atlas are separated by approximately 120 degrees. If you've ever looked at a blueprint for a satellite or a mechanical stabilization engine, you know that this is the golden ratio for balance. It creates a perfect equilateral triangle of force. If you wanted to keep a rotating object from wobbling as it drifts through the darkness, this is exactly where you would place your thrusters. Now, the official word from some researchers is that we should be careful. They suggest that 3I Atlas might be a contact binary, a cosmic accident where two or three separate rocks crashed into each other eons ago at very low speeds and got stuck together. It's a common thing in our own solar system. They argue that if the soft spots or vents for gas happen to be located in just the right places on these joint segments, you could in theory get a pattern that looks organized. But then you have to face the cold, hard numbers. For three independent vents to be placed so perfectly at identical latitudes and separated by almost exact longitudes while activating with the same intensity, well, that's where the 0.2% comes from. That is 1 in 500. To put that in perspective, imagine walking into a dark room and throwing 3 darts at a wall and having them land in a perfect balanced triangle, not just once, but every time the object rotates. I don't know if Loeb's hypothesis is the final answer, but it's becoming harder to ignore the feeling that 3I Atlas is more than just a piece of interstellar debris. If it's not a miracle of natural geometry, then the 0.2% probability is a signpost, a signature left in the void by someone or something that understands the math of the stars much better than we do. The more we process the Hubble data, the more 3I Atlas feels less like a discovery and more like an encounter. The clock is ticking, and 3I Atlas is not slowing down. We are currently heading toward a massive milestone in this journey, a moment that will either confirm our wildest theories or shatter them completely. On March 16th, 2026, this interstellar anomaly will make its closest approach to Jupiter. This isn't just a routine flyby, it's a trial by fire. Jupiter is the massive guard dog of our solar system, a gravitational titan that doesn't take kindly to intruders. Its gravity is so intense that it can tear comets apart or sling them out into the dark void forever. This encounter will give us the answers we've been craving. NASA is already preparing the Juno probe, which has been orbiting the gas giant for years, to turn its sensors toward 3I Atlas. This will be the most intimate look we've ever had at an interstellar traveler, while it's still active and reacting to our sun. What gets me is the scale of it all. We have the anti-tail, a massive chaotic tail of dust stretching 100,000 kilometers back toward the sun. And then we have these tiny precise jets, only 24,000 kilometers from the core. It's a study in contrast that doesn't quite add up. On one hand, you have the massive, messy tail of a typical comet, but on the other, you have the surgical precision of a machine. Some astronomers wonder if 3I Atlas is shedding its outer layers as it approaches Jupiter, revealing a core that was never meant to be seen. One hypothesis is that the object is a contact binary, but as we've discussed, a contact binary doesn't explain how those jets stay so perfectly balanced under extreme stress. Think about what Jupiter does to visitors. We've seen it before, most famously with Shoemaker-Levy 9, which was ripped into 21 separate pieces by the sheer force of Jupiter's gravity well. If 3I Atlas is just a loose collection of ice and dust, March 16th might be the day it breaks apart. But if it maintains its structure, if those 3 symmetrical jets continue to fire with that same 120-degree precision, even as the planet tries to tear it limb from limb, then we are looking at something far more complex than a rock. We might be looking at a deliberate act of navigation. We will see non-gravitational acceleration, just like we did with Oumuamua. If 3I Atlas makes a course correction as it passes the King of Planets, it won't just be a mystery anymore. It will be a message. I can't shake the feeling that Jupiter is about to act as the ultimate witness to something we aren't prepared to understand. We are watching a visitor drift through a gateway, and what happens next could redefine our place in the silence of the cosmos. I sometimes think we underestimate how quiet the universe can be. We spend our lives surrounded by noise, but out there in the void, the only thing that matters is the math. 3I Atlas is a puzzle written in the language of geometry and probability. Whether it's a 1 in 500 fluke of nature or a sentinel from a civilization we will never meet, it reminds us that we are small and our understanding of the darkness is still so fragile. We will be waiting for the data from the Juno mission in March, hoping that the silence finally gives us an answer. If you found this exploration into the 0.2% fascinating, please consider subscribing to the channel and leaving a like. It really helps us continue these deep dives into the unknown. If you feel like supporting our work even further, you're always welcome to become a member of the Cosmic Unknown family. The stars are waiting, and so are we. Stay curious, stay reflective, and as always, keep looking at the stars. But before we move forward, let me show you exactly what Hubble saw, because the images themselves tell a story that words can barely capture. The raw Hubble images show 3I Atlas as a bright, fuzzy blob. The inner coma is so brilliant it washes washes out everything around it. Just this glowing sphere of light with a smooth fall-off in brightness as you move away from the center. To the untrained eye, it looks like every other comet ever photographed. A symmetric, featureless cloud. Nothing special. Nothing unusual, but that brightness is hiding everything. The nucleus is buried under its own glow. All that gas and dust streaming off creates this haze that obscures the source. It's like trying to see through thick fog. You know something's there generating the light, but you can't see the actual structure. So the Hubble team ran processing on it. The first method strips away the smooth background brightness, so sharp features become visible. You're basically turning down the glare in the center so the fainter stuff around it shows up. The second method enhances anything that changes sharply, suppresses anything that's smoothly varying. Perfect for finding jets because jets are narrow, linear, distinct from the diffuse coma. And these methods don't create data. They reveal what's already there, but hidden, like adjusting contrast to see faint writing. The writing was always on the page. You just made it visible. Processing runs. First pass, the smooth glow starts breaking up unevenly. Brighter regions appearing, fainter regions, asymmetries. Second pass with the enhancement filter. And boom, there they are. Lines. Straight lines shooting out from the inner coma. Count them. 3 distinct jets. Maybe more, but 3 are unmistakable. Look at how they're arranged though. Not random directions. Not spraying everywhere. They radiate from a common center. They're narrow. They stay collimated as they extend outward instead of spreading out. They have specific angles you can measure. This is organized. The symmetry is what stops you. Pull back. Look at the whole pattern. The jets appear in a triangular configuration, roughly symmetric around a central point. Not perfect. Comets are messy, but close enough that it's obvious something's organizing this around a preferred geometry. The angles themselves, the spacing between the jets, it's running at approximately 120 degrees between each jet. Wait. 120 degrees. That's the angle of an equilateral triangle. That's the geometry you use when you want perfect balance, when you want 3 forces to cancel each other out and create stability. Multiple wavelengths, multiple telescopes, multiple dates, all showing the same organization. Comets have jets. Sure, that's normal. Active regions heat up, ice turns to gas, jets form. We've seen this on every comet we've studied close up. But 3 jets? This organized? Maintaining this exact geometry for this long? That's not normal. Because here's what should happen. Comet nuclei spin, usually every few hours or days. As it rotates, different parts face the sun, heat up, become active. Jets turn on, turn off, sweep around as the nucleus spins underneath them. You see them move, change position, create spiral patterns in the coma. 3I Atlas jets aren't doing that. Same orientation every observation, same pattern, same angles. Either it's rotating incredibly slowly, like weeks or months per rotation, or something else is keeping these active regions locked in position. And whatever that is, it's maintaining 3 symmetric jets along a consistent geometry for over a month now. You can separate the jets from the main dust tail easily. The tail, that broad diffuse structure, follows predictable physics. Sunlight pushes dust, creates a tail pointing away from the sun. You can calculate exactly where it should be, and it's there, right where expected, along with a faint anti-tail from dust left behind in the orbital path. But the jets aren't following that geometry. They're not aligned with the sun direction. They're rotationally controlled, organized around the spin axis of the object itself. Internal structure driving emission, not external pressure organizing dust. So we've got visual confirmation of 3 jets. Geometric analysis showing triangular symmetry. Position angles matching the 120-degree spacing. But how do you prove this isn't processing artifacts? How do you confirm these are real and not something the algorithms created? You measure, you quantify, turn the visual into numbers. Hubble teams ran a full circular brightness profile around the nucleus. Draw a circle around the central coma. Measure brightness at every point. Symmetric coma gives you smooth curve, same brightness all around. Real structure gives you peaks. They plot it. Brightness versus angular position. The curve isn't smooth. It's spiked, sharp peaks at specific angles, each one matching a jet location. The peaks are obvious. Discrete brightness increases at predictable intervals. This is proof. The jets are real. They're bright enough above background that they show up as distinct features in the measurements. This is how you separate signal from noise. Random fluctuations create noisy curves with small irregular bumps. Processing artifacts might create one or two features in specific spots related to detector quirks. But three distinct peaks, evenly distributed, matching the visual features, that's real structure. That's organized emission from the object. Different processing methods give same results. Different people working independently find same jets. The brightness profile confirms what the images show. You're not debating whether they exist anymore. You're trying to figure out what they mean. Hubble gave us structure, but structure doesn't tell you composition, doesn't tell you what's actually venting off this thing or why it's behaving this way. For that, you need spectroscopy. Split the light by wavelength. See what molecules are emitting, what's actually happening chemically. That's what other observatories did in the weeks surrounding the Hubble observations. Spectroscopic data shows clear emission lines, not continuum, not just reflected sunlight. Emission. Light emitted by excited molecules in the coma. Three species confirmed: cyanogen, Cn, diatomic carbon, C2, triatomic carbon, C3, all carbon-based, all common in comets, all products of organic material being broken down and sublimated under heating. Cn is particularly useful as a tracer, created when complex carbon-nitrogen compounds break apart. Parent molecules in the nucleus, things like HCN or other organics, sublimate and get dissociated by solar UV. Fragments include Cn radicals glowing at specific wavelengths. You detect Cn. You know there's carbon-nitrogen chemistry. You know the nucleus contains organic material. C2 and C3 are pure carbon chains, come from even more complex carbon compounds breaking into simpler fragments. They fluoresce green under UV, which is why comets often look green. That classic green color isn't exotic elements, just carbon chains glowing. Strength of emission tells you how much carbon-rich material is sublimating. 3i Atlas shows strong C2 and C3 emission, lots of carbon coming off. Compared to solar system comets, Cn, C2, C3, these are standard molecules. Every comet shows these. Halley, Hale-Bopp, Hyakutake all had strong carbon chemistry. So composition-wise, 3i Atlas isn't exotic, not weird interstellar material we've never seen. It's ice and organics. Same as solar system comets. Interstellar space and solar system formation produce similar basic chemistry, at least for comets, but behavior is unusual. Organized jets, stable rotation, persistent geometric structure. These aren't standard traits, even though chemistry is standard. So it's not made of something different. Something about structure or rotation or activity pattern is different. Same materials, different organization. The green color connection ties everything together. Ground observers in December reported green coloration in the outer coma. We mentioned this before. Color evolution from blue to green to gold. The green phase, that's C2 and Cn emission. Spectroscopy confirmed the molecules responsible. When amateurs were imaging and seeing green, they were seeing carbon chemistry, real molecular emission, and timing matters. Spectroscopic observations happened around the same time as Hubble imaging. The chemistry detected was already there, already active, already producing emissions that would create visible structure-ground telescopes later resolved. Molecular emission feeds coma. Coma develops structure. Structure persists because emission source, those active regions creating jets, stays organized. Stack observations chronologically and watch the picture develop. July 2025. Discovery during gamma-ray burst event. Object appears faint and red. November. Perihelion passage. Color change detected. UV structure observed. Chemistry confirmed. December. Ground observations reveal stable directional feature. Hubble resolves jet structure. Full geometric and spectroscopic characterization achieved. Every observation adds a piece. Every piece fits. You're building a coherent model where an interstellar object with weathered surface approaches Sun. Gets stripped by heating, exposes fresh volatile material. Active regions create jets. Jets organize around rotation axis. Chemistry confirms carbon emission. Structure persists across weeks. What we know for certain. Organized jet activity confirmed by Hubble. 3 distinct jets in triangular symmetric pattern. Geometry orientation approximately 120 degrees between jets. Consistent across multiple independent measurements. Post-perihelion surface renewal confirmed by color change toward blue. Indicates fresh material exposure. Active chemistry confirmed by spectroscopy, CN. C2, C3 emissions, strong carbon-based outgassing, gas-dust separation confirmed by wavelength-dependent morphology. Blue shows gas, red shows dust. Different distributions indicate active separation. What's still not fully explained? Why is the geometry so precise? 3 jets at exactly 120 degrees is the configuration you'd use for perfect balance, for stabilization, for controlled thrust in 3 directions that cancel out to maintain orientation. Natural comets don't typically show this level of geometric precision. They show chaotic, irregular jet patterns, multiple jets at random angles, asymmetric activity that causes the nucleus to tumble and precess. 3I Atlas shows none of that chaos. It shows order. Precision, stability. Why don't jets sweep around more obviously? If the nucleus is rotating with periods of hours or days, jets should visibly change position as active regions rotate into and out of sunlight. We're not seeing that variation. Jets appear stable. Why such high activity level for such a small object? The amount of gas being produced, the brightness of the jets, the size of the coma, all suggest an object that's much more active than its size would predict. Small comets typically have low activity. They don't have enough surface area or enough volatile material to produce dramatic displays. But 3I Atlas is punching way above its weight class. Why this specific geometry? 3 jets in symmetric pattern around 120 degree spacing. That's organized. Comet nuclei are irregular chunks, not precision objects. Getting this symmetry from random surface features and natural outgassing is possible, but unusual. These questions aren't showstoppers. They're next-level investigation. You've confirmed basic structure, chemistry, activity pattern. Now you refine, model, explain details. Figure out what makes this particular object behave this way when most comets show more chaotic activity. And while this develops with 3I Atlas, we need to talk about what happens next. Because the Jupiter encounter isn't just about seeing if the object survives, it's about testing whether the geometric structure persists under extreme stress. Jupiter's gravity will create tidal forces. The side of 3I Atlas facing Jupiter will feel stronger gravity than the side facing away. This creates stress, tension, forces that try to pull the object apart. If 3I Atlas is a loosely bound rubble pile, those tidal forces might be enough to fragment it. We'd see pieces breaking off, debris clouds forming, the object coming apart as Jupiter's gravity overwhelms the weak forces holding it together. But if the object has structural integrity, if it's held together by something stronger than just weak gravity, it will survive intact. The jets will keep firing. The geometry will persist, and that persistence would tell us something important. It would tell us this object isn't just a random collection of ice and rock. It has structure, strength, organization that can withstand forces that would tear apart normal comets. The magnetic field interaction is another test. Jupiter's magnetosphere is the largest structure in the solar system. It extends millions of kilometers from the planet. It's filled with charged particles, plasma, intense radiation. When 3I Atlas passes through this environment, if it has any magnetic properties, if it's carrying any charge, Jupiter's field will interact with it. We'll see disturbances, ripples in the magnetosphere, changes in the plasma environment. Juno's magnetometer will detect these interactions. The spacecraft has been studying Jupiter's magnetic field for years. It knows what normal looks like. Any anomaly caused by 3I Atlas will stand out. And if we detect magnetic interactions, that tells us the object has properties we don't expect. Comets aren't supposed to have strong magnetic fields. They're too small, too cold, too simple. A magnetic signature would suggest internal structure, maybe a metallic core, maybe active field generation. Either way, it would be significant. The trajectory change is the final test. We've already seen 3I Atlas make course corrections, small deviations from purely gravitational paths, changes that suggest non-gravitational forces are acting on it. If it makes another course correction at Jupiter, that's a pattern. Once is an anomaly, twice is suspicious. 3 times is a signature. And if those course corrections happen at specific points in the trajectory, if they're timed to optimize the path through the solar system, that's when conventional explanations start to fail. Because natural outgassing doesn't produce optimized trajectories. It produces random perturbations, small changes that accumulate over time but don't follow any particular pattern. Optimized trajectories require planning, calculation, intent, and intent is the one thing natural objects don't have. So March 16th isn't just about watching a comet fly past Jupiter. It's about testing hypotheses, about gathering data that can distinguish between natural and artificial, about seeing if the patterns we've detected continue or break. The geometry is real. The 120-degree spacing is confirmed. The chemistry is active. The structure is organized. And in 3 months, we'll see if it's all just an incredibly unlikely natural phenomenon or something more. The Hubble images have given us the clearest view yet of what's inside 3I Atlas. And what's inside doesn't look like any comet we've ever seen. 3 jets, perfect triangular spacing, stable geometry, active chemistry, all happening in an object that's traveled billions of years through interstellar space to arrive in our solar system at this exact moment. The probability of all of this being random is 0.2%, 1 in 500. Those aren't good odds for coincidence. Those are odds that make you ask uncomfortable questions. Is this the strangest natural comet in history, or is it something else? The data doesn't give us a definitive answer yet, but it's pointing in a direction that's hard to ignore. Hubble saw what's inside 3I Atlas, and what it saw defies every law of nature we thought we understood about comets. The jets are real, the geometry is precise, the chemistry is active, and the object is heading toward Jupiter. In 3 months, we'll have more answers, or more questions. With 3I Atlas, it's impossible to predict which. But one thing is certain. This object is teaching us that the universe is stranger than we imagined. That interstellar visitors can carry surprises we're not prepared for. That geometry and probability can sometimes point toward conclusions we're not ready to accept. The 0.2% is real. The 3 jets are real. The 120-degree spacing is real. And whatever it all means, we're about to find out. Stay tuned, because the Jupiter encounter is coming, and when it does, 3I Atlas will either confirm it's the most unusual natural object we've ever studied, or it will force us to reconsider everything we thought we knew about what's possible in the cosmos. Thanks for watching. Subscribe for updates, and keep looking up, because the universe is full of mysteries, and 3I Atlas is proving it.